Hey, Chem 30, welcome to topic number 3 of unit number 5. We're going to take a look at strong acids, strong bases, weak bases, and know the difference between each of those things, as well as a little bit of acid nomenclature review that you would have seen in grade 10 and grade 11. So first, we have to recognize that there are more than one type of acid. So there are binary acids and what I call complex or oxyacids. So binary acids, as the name suggests, is made up of two ions, one of them being hydrogen and then an anion. So they're basically the anions that we're going to see are from the right-hand side of the periodic table, the non-metals, right? So for example, chlorine or fluorine, bromine, sulfur, that kind of thing, across that staircase. These ones are simple to name them. We just add hydro at the front, the root name of the anion, and then add ic at the end. So we get hydrofluoric or hydrobromic. Okay, so again, made up of only two parts. We've got the hydrogen and this anion. This anion could be anything, chlorine, bromine, fluorine, so on and so forth. Okay, there are a couple of exceptions to this. We do not call it hydrosulfuric acid. We call it hydrosulfuric acid. So we don't drop the ending of that sulfur. We keep that, so the root name and the end, because it just flows better. Same thing with phosphoric acid. We don't call it phosphic acid. We call it hydrophosphoric acid. So this would be, if we had a binary acid, this would be hydrosulfuric, and this would be hydrophosphoric or phosphoric acid. All right, we're just gonna name 3 through 6 here. We get hydrochloric acid. We just keep on adding that that ic at the end there. So then we get hydrobromic. This is hydroiodic acid. And then this is one of our exceptions, hydrophosphoric acid. So we just keep that 4 part. We don't drop that. All right, pretty straightforward with binary acidic compounds. When we're writing the formula of these compounds, we have to recognize that hydrogen is always a +1. So we just figure out the charge of the anion and add however many hydrogen we need to balance that out. So nitric, we should recognize that this comes from nitride. So nitride is N3 minus, so this would be H3N. And then hydrobromic acid would be, this is Br, so this would be HBr, and we're done there. Now, you might be thinking, hey, wait a second, H3N, I've never seen that. No, really, it's NH3, and that's actually a base. But based on the rules that we're using, we'd call that hydronitric acid, H3N, okay? There's not going to be an example like that. So if that's a little confusing, don't worry about it too much. Complex acids are acids where hydrogen is combined with a complex anion, usually an oxyanion. That's why sometimes these are called oxyacids. So in all these examples, you'll see that oxygen is always there. Another example would be HClO4 or HClO3. There we go. H2CO3, right, carbonic acid. So it's hydrogen combined with a polyatomic, and the list of polyatomics, remember, is in your reference book right at the top of that periodic table of ions. So when we're naming these, we have to know the name of the anion. Once we know the name of the anion, we change that and add either us or ic and an acid. Us changes to ite, and ate changes to ic. So an easy way of remembering this is I ate an icky apple, and the snake's bite was poison us. So ite changes to us, ate changes to ic. So if you look down the list on your periodic table of ions, starting at the top, acetate, arsenate, arsenite, benzoate, borate, bromate, carbonate, we see that there's lots of eights, and then there's chlorite and sulfite, nitrite, right? Those ite endings change to us, and they're a little bit less common than the ate, which changes to ic. So I've shown you the steps here for the first 3. So I've identified the polyatomic as being sulfate, ends in ate, so I change that to ic and add acid, so I get sulfuric acid. HBrO3 is the anion is bromate. Bromate changes to bromic. And HClO2, I see it's chlorite, so it changes to chlorus, so chlorous acid. PO4 is a phosphate ion. So we call this phosphoric acid. And you might be thinking, we just called something phosphoric acid. No, we called it hydrophosphoric acid. So hydrophosphoric acid tells us that it's only made up of two elements, hydrogen and phosphorus, and that works out to be H3P. But phosphoric acid, I named that wrong, phosphoric acid in this case is involving the phosphate ion, which is different, right? So then this one becomes, it's the nitrate ion, which becomes nitric acid. Then we've got this NO2, which is the nitrite ion, which becomes nitrous acid. And then HSO3, that's the sulfite. So this is sulfurous acid. Okay. We're going to write the formula of these, and then we're done the review part of this. So chloric, we have to recognize the chloric comes from chlorate. Chlorate is ClO3 minus. We just need enough hydrogen to balance this out. So we can recognize that that's a -1, so this must be just that, one hydrogen to balance that out. Sulfurous, this means that we had the sulfite ion. Us comes from ite, right? So this is SO3 2 minus, so H2SO3 is the formula of sulfurous. Nitrous means that we had that nitrite ion. Nitrite is NO2 minus, which makes this HNO2. And then bromic acid, we should recognize that comes from bromate, which is BrO3 minus, which gives us the formula HBrO3 for bromic acid. All right, that is the review. That's really quick, but hopefully that was just review for you as well, and you already know most of this material. Okay, on to Chem 30 stuff here. First, we're going to classify, or another way of classifying acids is by the number of hydrogens they donate. So monoprotic acids donate 1, polyprotic acids donate usually 2 or more hydrogens. An example of that is sulfuric acid or phosphoric acid. Poly meaning many, okay? So it's that all-encompassing term. We also can classify acids as being diprotic and triprotic. So di meaning 2, they donate 2 hydrogens, and triprotic meaning 3. So we can call both of these, they're both polyoprotic. This one here, this H2SO4 would be diprotic, and this H3PO4, phosphoric acid, is triprotic, okay? So protic just refers to a proton being donated, right? So when we have hydrogen plus, normally hydrogen is made up of 1 electron and 1 proton. But when it's H plus, that electron has been transferred away. So really hydrogen is just a bare proton. That's why we call it protic. Okay, so monoprotic acids give off 1, polyprotic acids give off more than 1. When we have a polyprotic acid, it actually ionizes in steps, meaning that it gives off 1 hydrogen at a time. We can see this here that H3PO4 dissociates or ionizes to make H2PO4 and H3O plus. We could write this as H plus. So 1 is given off there. Then that species comes down here, donates another one. So we got another H plus. And then this one comes back down here, donates a third one. And then we have an H again, right? So it keeps on giving off H plus at every step of the equation here. So important to recognize that each time that it happens, this number here gets smaller and smaller, the Ka, that constant. We're going to talk about Ka a little bit more specifically later on, but the Ka is essentially the strength of the acid. So if we think about KSP, the larger the KSP, the more that dissolve, right? The more that turned into the products. So we can see as we go down the line here, this number is getting smaller and smaller by about a magnitude of 5, which is 10,000. So this process is about 10,000 times greater than this one, which is 10,000 times greater than this one, which makes this about 1,000,000 times or 100 million times more likely or stronger of an acid. Okay, so every time we pull off a hydrogen, the acid gets weaker. And the reason is because essentially Hess's law that once we have lots of H plus here, it's going to drive this equilibrium reaction backwards there in further steps. The big thing to note here is that triprotic acids don't donate all 3 of them at once, just 1 at a time. All right, the strength of an acid is the extent or the measure of how easily it produces its ions. Okay, so if we had a strong acid here, it would entirely produce ions over here. So there'd be none of this left. Okay, so all the ions, it moves entirely towards the ions. Okay, it is represented by a single arrow, meaning that it's only a one-way reaction. It's irreversible. The ions don't reconnect. So no matter what in solution, you know how in KSP we said, okay, well, it makes ions and we've got some, let's say H plus and Cl minus. At no point do these ions ever rejoin and make an HCl over here. They don't go through this endless cycle. The water is more, these ions are more stable in water as they're ions, and in turn, they do not want to be reconnected. Okay, so this statement here, HA is equal to H plus. That means whatever acid, the general form for an acid is HA, because all acids are comprised of hydrogen and an anion. So let's say that we had HCl breaks down into H plus and Cl minus. If this was 1 molar, the concentration of the H ion would also be 1 molar. If we had HBr, this is another strong acid, and this was 6 molar, the concentration of H plus would be 6 molar, and the concentration of Br minus would be the same, but we just don't really care about that generally. There are 7 strong acids, 3 of which are binary. So hydrochloric, hydrobromic, and hydroiodic. The bottom 3 of group 17 of the halogens, right? So it goes fluorine, chlorine, bromine, iodine. Chlorine, bromine, and iodine are all strong acids. Then if we cross those out, we can see that we've got 2 chlorine or chlorate-based ones. This one here is called perchloric acid. And this one here is called chloric acid. In chemistry, when we have 4 oxygens, we generally use the per prefix, right? We'll see permanganate is another example of that. So we call it perchloric acid and chloric acid. Then we just have 2 others. This one here is nitric acid and sulfuric acid. You have to memorize these 7. There's really not too much of a trick on this. I've tried to scour the internet trying to find an acronym or something that might help you, but it really just works out to be, okay, there's 1, 2, 3 chlorine-based ones, or there's 1, 2, 3 binary, 2 chlorine, and then 2 oddballs here. Now, you'll notice that there's only 1 acid on here that's diprotic, so H2SO4. When we write H2SO4, this is kind of a special one. We do actually write this as protonating twice. So if the concentration of this is 1 molar, the concentration of the H plus is 2 molar, because 1 molar or 1 molecule of H2SO4 will break down into 2 hydrogen ions. The Ka, the strength of that acid, even the second version of it, is so strong that it does happen, or at least for this class, we'll consider it to be happening. Okay, so just make a note of that. Okay, so in solutions, all of these ions or these compounds will directly form their ions. Whatever the concentration of the original acid is equal to the concentration of that H plus ion. We're going to see that later on more in depth. Strong bases. There are 8 strong bases. If you know your periodic table well, or your elements, it sort of looks like this, right? So we get this shape here. The first column here and the next 3. So 5 down and 3 up. So we got lithium, sodium, potassium, rubidium, cesium, calcium, strontium, and barium hydroxide. Those are our 8 strong bases. It's easy enough because to name these, all we add is the cation, so the name lithium, and then hydroxide at the end. So we got lithium hydroxide, sodium hydroxide, potassium hydroxide, so on and so forth. Okay, and it's easy enough to remember because it goes down 5 and then up 3. So just look at your periodic table and scout out that. The thing to note here is that these 3 elements, calcium, strontium, and hydroxide, when one of those breaks down, it actually produces 2 hydroxide ions. So let me give you an example. LiOH breaks down into Li plus and OH minus. We know this is a strong base, so the concentration of the base is equal to the concentration of the hydroxide ion. If this was 3 molar, this would be 3 molar as well. Now, for these last 3, the elements in that second column, which are called the alkaline earth metals, they actually produce 2 of these. So if this was to break up into calcium 2 plus and 2 OH minus, if this was 2 molar, this would be 2 molar, this would be 4 molar. Because for each one of those calcium ions, it forms 2 of those hydroxide ions. Okay, and the reason why this happens is because these are extremely polar bonds, which water can easily manipulate or pull apart. We talked about that in Unit 1. Okay, weak acids and weak bases are different because they ionize less than 50% in solution. That means if we had concentration, for example, of this guy here, if the concentration of CH3COOH, and we write this with an equilibrium sign because it's going back and forth. These ions are very much doing the same thing as those KSP ones where they break apart, they reconnect, they break apart, they reconnect, and that process is endless. So if this was 1.00 molar, once equilibrium has been established, this drops down to something like 0.99 molar, and this works out to being 0.01, 0.01. Okay, so it's mostly that acid that stays in solution, that molecule version of it, right? So there's very little H plus created. That H plus is what makes an acid acidic, right? Solutions are acidic because there's lots of H plus floating around. So if we're comparing the strong acids back here and the weak acids over here, we can see that the amount of H plus being created in both of those solutions, 1 molar of HCl means we got 1 molar of H plus. 1 molar of acetic acid means we've got 0.01 molar of H plus. We can see there's a lot less H plus being created, which makes it a weaker acid. Okay, so many organic acids will have the carboxylic functional group. In our class, almost all of them will, and they exist as an equilibrium between the molecule form and the ion form. So this is our molecule form, and this is the ion form. Okay, so these ions are what make it acidic. So if we can make more product, if we can go this way, we make the solution to be more acidic. If we have it going in that direction, or we move the equilibrium back towards the reactants, we make the solution less acidic. All right, the reason why this exists, why these acids are considered to be weak, is because they have almost non-polar bonds. They're built differently, right? So they're polar covalent as opposed to ionic, which means that water can't dissociate or pull them apart as easy. Okay, and then we have to also recognize that not all acids and bases are strong or weak. There's really kind of a spectrum here. They can be strong in certain situations and weak in other because temperature and concentration of the solution affects their strength. What we're going to this is a nice little diagram of the difference between strong and weak. So these are considered our A minus. Okay, so we can see that there's almost, or there is no molecule version of these anymore. They completely dissociate into the A minus and the H pluses. So we can see that there's lots of H plus, which makes this very acidic, we'll say. So very acidic. Now, in this one, we can see, yeah, there is some H plus, but mostly molecule. This one is the ion form, ions there. But we can see that there's a big difference. In the left-hand side, we can see that it's only ion form, but on the right-hand side, we see mostly molecules still. And there are a couple of ions floating around. Okay, so it means that there's much less hydrogen. Much less hydrogen means it's much weaker acid. Alrighty, so organic acids have the carboxylic functional group. So this functional group right here, that functional group, this hydrogen is the only one that comes off. So even though we see that there's 4 hydrogens here, it's only this hydrogen here that can break off. Okay, so we'll see more complex versions of this in just a second. I'm going to show you, but it's really important that we recognize that only the one hydrogen comes off and which one we're going to be doing. So when we're writing dissociation equations, it's not the CH3COOH breaks down to form H plus and CH2COOH. Okay, so we got to be really careful about that. We don't want to make that silly mistake. Okay, let's look at a couple of organic or weak acids for us. So the simplest one, if you recall back to the organic chemistry unit, we have methane, ethane, propane, and butane. Well, the acid version of those, the version of those with a carboxylic functional group is methanoic to ethanoic, 3, propanoic, and 4, butanoic. Now, interestingly, as we move across that line, they actually become weaker and weaker acids because the molecules themselves are made up of more of a non-polar component and then a small polar end. So methanol, very small, 1 carbon. It's exclusively, it's a very polar molecule because it's so small and only made up of 1 carbon. So the carbon and the hydrogen make it non-polar, but the functional group that's attached to it makes it polar. So the more of that entire molecule that's made up of the functional group, then more acidic it becomes. So methanol, just 1 carbon, and then we've got this double bond oxygen, this OH group, and then the remaining H like this. And we'll see this often written as HCOOH. Now, this H here is this part, and then this is the functional group. So if we're looking at how this ionizes, HCOOH, aqueous, and we draw that double arrow because we've got a weak acid, breaks down into H plus aqueous and HCOO minus aqueous. And we can see that this is the hydrogen that protonates. 2-ethanoic acid, very similar. We get carbon connected to carbon. There's our ethane backbone. Here's our double bond oxygen. And then we just fill in the remaining with hydrogen. And we see that both carbons have 4 bonds. This formula would be, we see it sometimes as H3C. So we write that the hydrogens first, so then the 2 carbon units are bonded to each other. So it shows it. Sometimes we'll see it written like that, but most of the time we see acetic acid written as CH3, that first unit, and then we've got that COOH, the second unit. So when that decomposes, we get CH3COO minus and H plus. Again, we can stack this, all the carbons, right? So we could have C2H4O. 2, but this is weird because we don't know how many hydrogens it can actually protonate. So we get this one here. This is generally the way you'll see it written. Propanoic acid, very similar, 1, 2, 3 carbons, and we get that double bond oxygen, single bond OH, and then we fill in the remaining with hydrogen again. So in this case, we get CH3, CH2, COOH, which ionizes to form CH3, CH2, COO minus, and H plus. And we just keep on continuing this pattern. Butanoic acid would be CH3, CH2, CH2, COOH, which breaks down into CH3, CH2, CH2, COO plus H plus. Right? So its bond line would look like this. We got our 4, and then on this last carbon, we're going to have our OH group and a double bond. Oh, right. So there's butanoic acid. We can get more complex versions of these. This one here is called benzoic acid. So remember, a benzene is this structure here where we have 3 double bonds, right? So it's a cyclohexane with 3 bonds. So we normally call it 1,3,5 tricyclohexatriene or something along those lines. But instead, we just call it benzene. And if we have this carbon this carboxylic functional group, instead of calling it benzene, we call this benzoic acid. It actually has the formula C6H5COOH. No, that's not true. No, that is H5COOH. Sorry, my bad. That is correct. Okay, so this C6H5 refers to this structure here, but instead of having a hydrogen on this one, we've got this COOH functional group. Okay, so those are some common examples of those weak acids, and repeatedly we see that it always breaks down into C6H5COO minus and an H plus. Okay, so these are all monoprotic weak acids. There are some triprotic weak acids. For example, if we just consider this structure here, we would have this OH, then we've got this double bond O, and then we've got the same thing on this one up here. This would be a diprotic acid. This would be C6H4 bracket COOH 2, because we can see that we've got 2 of those functional groups, and it breaks down into 2H plus and C6H4 COO. And then we'd write a little 2 here, negative, and 2H plus. Oh, we already had that 2H plus. So it's a little bit more complicated. We're not going to see anything like that. We're not going to take into account any diprotic weak acids. We're not going to, that's not going to play a role in our chemistry. It does in other ones, but for us, that's not a thing. Okay, so weak bases, on the other hand, have the amine functional group. So remember our definition based on the Brownson-Lowry definition, which is the only definition we can use to sort of account for the nature of weak bases, is that bases accept hydrogen. So basically what happens here, these lone pair of electrons, instead of having that lone pair, a hydrogen can attach itself there. So it accepts this hydrogen. So anything that has a nitrogen with two lone electrons or two electrons can act as a base. So this one here, this guy's called pyridine. And you can see it in your chart. We have Ka, a table of weak acids and a table of weak bases. This here is aniline, the other substance. So we got that functional group here. Now, it's a little bit, pardon me, tricky because these structures, the nitrogen might have more than one hydrogen or no hydrogen at all. Okay, so we call these primary, secondary, and tertiary amines, but it's a little bit trickier to function or to notice what's happening. So I'll give you an example here. Let's imagine that we've got methylamine. So methylamine, we're going to have our regular methyl group. So here's our methyl group, and then a nitrogen. Now, nitrogen, in order to be happy, needs to have 3 bonds. So it generally looks like this. So 1, 2, 3. So it's got the, oh, that's too many, 3 bonds. It's got 1 to the carbon and then 2 hydrogens and a lone pair. This is what we call methylamine. Methylamine. Now, the hydrogen would attach right there, but this has got the formula CH3NH2. So when we put it into water plus H2O makes CH3NH3 plus aqueous and OH minus aqueous. We can see that one of the hydrogens has moved from the water to the methylamine. Okay, so the reason why this is a little bit tricky, this is what we call a primary amine. Why is it a primary amine? Because it's connected to one other carbon. Let's look at another version of this. So let's say that we've got a methyl group here, so CH3, and then we've got this, and then we've got, oops, another carbon here. So it's CH3, CH3, and nitrogen, remember, needs 3 bonds. So we put a nitrogen or a hydrogen there, and then we've got the lone pair. This is what we call dimethylamine. Pretty easy to see why 2 amine groups, right? So in this case, its formula is CH3 2NH. Okay, and it works the same way. So instead of having 2 hydrogens, but because it's connected to 2 carbons, we call this a second degree amine. And when it picks up or reacts with water, it's going to make CH3 2NH plus and OH minus. You can see that the number of hydrogens has increased by 1. Okay, the last example, I'm going to just clear the slide here, is imagine we've got a nitrogen in the middle, and I've got a CH3 group here, and I've got a CH3 group here, and I've got a CH3 group down here, and then I have the lone pair up top. This is what we call a tertiary amine. And it's going to have the formula, bracket, CH3, 3N. And this is trimethylamine. What is it going to do? It's going to do the same thing. We add it to water, and we get CH3, 3NH plus. So we just keep on increasing the number of hydrogens by 1. So it had none to begin with. It's got 1 more and OH minus. Okay. So if you look in your reference book here, and you look on almost the very last page, you'll notice a chart of bases at the top. And they either have something we'll call RNH2, RNH, or RN. Each one of these, always, all we really do is when we put them in water, they become R, oops, let's try this one more time, R bracket NH3 plus, R NH2 plus, or RNH plus. Okay, depending on what the original formula is. Hopefully that makes sense. All right. The the next sort of thing that we have to imagine here is the terms dilute and concentrated. And we saw this in the last unit when we're talking about solutions. A dilute solution is a weak solution, concentrated is strong. We can have a dilute strong acid or a dilute weak acid, because dilute refers to the number of solvent and solute particles, not to the strength. Okay, so there's a nice little, there's 4 images that you're going to see here in just a second. Each soldier is referred to as a particle. Okay, so a soldier represents a particle, the molecule version of it. If it's an ion, if it turns to an ion, it has its little sword up, and if it has its sword in its holster, it's the little sword pocket thing there, it's considered to be still the molecule. So in this one here, we've got a concentrated and strong solution, right? We've got lots of particles, right? We've got lots of soldiers, and each one of them has ionized. So this is something like 12 molar HCl. This is very strong. This is about as strong as it gets. You can have 18 molar H2SO4. This right here, these 2 solutions, if you had these strengths, you'd be able to, if you got it spilled on your skin, it would eat your skin away very quickly, very dangerous. Okay, so this is a concentrated and strong solution. Now we've got a concentrated and weak solution. Although we have lots of soldiers, not very many of them have ionized. And a good example of this is something called glacial acetic acid. Glacial acetic acid is a concentrated form of CH3COOH, acetic acid, right? So it's a very concentrated, and I'm not sure what the molarity would be. But even though we've got lots of soldiers, not very many of them turn into ions. So we've got lots of soldiers, but not very many of them turn into ions. Okay, so now we've got a dilute strong acid. So an example of this would be something like 1 molar HCl. We don't have very many soldiers, but all of them have got their swords out. We can see that. So all of them have turned into ions. And then finally, we've got a dilute and weak acid where we don't have very many soldiers, and even fewer of them have ionized, have got their swords out. Okay, so the most dangerous or the scariest thing would be a concentrated strong solution. Why? Because there's lots of soldiers to do damage, and each one of them has turned into ions. Where the least dangerous is dilute weak acids, because there's not very many ions, and there's not very many particles, and even fewer turn into ions. Okay, just a couple more slides here. So we're going to write acid ionization equations followed by base ionization equations. So recall that strong acids completely ionize, which means that they transform from HA to HNA. Generally, we see the states aqueous, aqueous, and aqueous. In this class, we're always going to see that. Weak acids partially ionize, so an equilibrium arrow is used because there's this transition from the molecule version of it back to the ion version, and then ions reconnect and then form that molecule. So the preferred state isn't exclusively the product, so they can move back and forth depending on the equilibrium conditions. Okay, so we use that HA equilibrium sign and then 2 aqueous substances. So we're going to write the ionization equation for hydrochloric acid and the ionization of carbonic acid. Now, I can choose, remember, that the Bronsted-Lowry and the Arrhenius model work for both of these acids. So I'm going to write one of each. So hydrochloric acid, I should recognize that as being one of my strong acids, so HCl aqueous. And I'm going to use the Arrhenius here because it's super simple. HCl breaks up into H plus and Cl minus. Boom, done. Okay. I'm going to use the Bronsted-Lowry for carbonic acid. So carbonic acid comes from carbonate. So carbonate is CO3 2 minus, which means I need 2 hydrogens to balance that out. So H2CO3. So I'm going to write H2CO3 aqueous is combined with water, right, using the Bronsted-Lowry. And that's a liquid, double arrow to indicate this is a weak acid. This protonates to HCO3 aqueous and H3O plus aqueous. Okay, again, fairly straightforward. We're just moving one of those hydrogens to the water. So recall that water is a amniprotic substance, which means it can gain or lose depending on what it's combined with. When it's combined with an acid, it's going to gain a hydrogen to form H3O+. Okay, if you wrote the Arrhenius or you used the Arrhenius model for that, totally fine. Doesn't make any difference here. All right, strong bases completely dissociate, so they turn from BOH, generally aqueous, into these two substances. Sometimes we'll see this as a solid. Strong bases, such as sodium hydroxide, can start as a solid and dissolve in water. So we'd see something like sodium hydroxide solid decomposes or ionizes to form Na aqueous and OH minus aqueous. You'll be given that hint in the question, right? So solid, or it would say solid sodium hydroxide dissolves in water, or it might say 40 grams of sodium hydroxide is put into water. So when we're measuring grams, we're generally measuring solids. Weak bases do the same thing. Recall, hopefully, that weak bases only work with the Bronsted-Lowry. So we're going to use the Bronsted-Lowry here and the Arrhenius up here. Okay, so the strong bases only work with Arrhenius, weak bases only work with the Bronsted-Lowry. So let's take a crack at this one. We're going to write the ionization equation for sodium hydroxide. We should recognize that as being NaOH, and the ionization equation for methylamine, which is a weak base. To confirm that this is a weak base, right, it's not part of the 8 strong ones that we know, but we can look on this in our reference book in that KB chart and see that methylamine is there. So we're going to use the Arrhenius. Arrhenius states that strong bases are those that break down to form OH minus ion. So NaOH breaks down to form Na plus aqueous and OH minus aqueous. Pretty straightforward. Nothing too surprising there. All right, let's take a crack at B, which is the methylamine. So we're going to take our methylamine, CH3NH2, recognize this is a weak base, which means we need to put it into water, so H2O. Water is always present in weak bases, so we're not really putting it into water. We're just including water in our ionization equation. So it's going to pick up that hydrogen from the water. Remember, water acts as an acid, a Bronsted-Lowry acid, when combined with a base. So we get CH3NH3 plus aqueous and OH minus aqueous. I need to include the state there. Alrighty, that's it for topic number 3. If you have any questions, please email me. Otherwise, have a great night, Chem 30.